So welcome everybody to Thursday's morning session, and my particular pleasure to introduce the first speaker. We know each other for some time, since he had his PhD in Freiburg with Dietmar Kröner. I was learning what a free boundary problem is from Gerd Juck and visiting Freiburg several times, and it was a big pleasure. Since then, Mario made significant contributions to the numerics of PDEs, as you all know, error estimation and model reduction and multiscale problems that we see model order reduction and multiscale methods are on this slide. Today we speak on localized model order reduction for parameter optimization with multiscale PDE constraints.
Yeah, thanks a lot for the introduction and for the organizers also for this follow-up workshop. This time I want to speak about recent work that we did in the last years, and for instance, a lot of this goes to Tim Kyle and his PhD thesis. For instance, we worked on model order reduction for parameter optimization with PDE constraints, and this was funded by the DFG, the German Science Foundation, in a project together with the group of Stefan Volkwein. And in the group of Stefan Volkwein, there was Luca Micheli contributing to this, and maybe you know that in my group, Stefan Rabe and Felix Schindler also work on these topics and were contributing. So let's go into this talk. I want first to recap a little bit, for instance, for the younger ones, the backbone of classical reduced basis methods as one of the tools in model order reduction. I will then go towards the main topic, which is the PDE constraint optimization, where first I will not step into the multiscale issue, but then I will do that in the last point, and there I connect to the famous local orthogonal decomposition method that we heard about a lot also in this workshop, and I will give one other small glimpse of how you can view this method and access it and use it also for model order reduction. So let's go into challenges. So I give you some background of projects that we were doing in the past years. So this is already some years ago where we worked in a project with different universities and groups on a battery simulation, and in that project it was resolved, which means that in the electrode you see you have these porous materials, and we actually did some high-resolution scans of these electrodes and did simulations in the pore geometry, because in these projects we were looking at degradation modeling, and one of the degradation processes is lithium-ion plating, which means that the lithium ions go into the metallic phase and they build dendrites, metallic dendrites, and this at the end can lead to a shortcut in the electric circuit, and this usually is what then lets this battery explode. So this is one of the most serious degradation processes, of course, and as we are mathematicians, we know that these processes, they are triggered in the high currents, and high currents occur in singularities, and singularities are due to singularities that come from the geometry in the micro scale. So if you have some sharp edges, then of course in these edges you may have singularities in the solutions where you have high currents, and we want to detect it, so you cannot go with homogenized models, and this puts quite a challenge. So another project that we just ended this year was together with Umicore. So this is a chemical industry partner where they do catalytic filters, and if you go into the catalytic filters, then you again see these porous layers where you have the flow through these catalyzed, and we wanted to do effective simulation for that. And in this project, we, for instance, combined model order reduction tools with machine learning methods in order to access these filters. I will not go to this machine learning part here, but just wanted to highlight this application. So then, last but not least, an application which is not accessible with easy tools was a joint work that we did with, for instance, Lorenzen and Oguntula from North. So this is a research institute in Bergen, and they are investigating in oil recovery, and this is enhanced oil recovery, so the third phase of oil recovery, and they wanted to optimize injection and production wells in order to get most profit out of this oil field. So this is the application behind, and this is a black oil model with a three-phase, four-component, multi-phase flow problem with a lot of nonlinearities interacting. So I will also not go into these details. And there we are also at the limit to do invasive coding with model order reduction, and we relied on combination of classical solvers, like here the OPM packages used with machine learning models to speed up these optimization processes. So let's go to model order reduction. So meanwhile, model order reduction is quite well developed. It has been a very active field in the last, let's say, 20 years, and its goal is to prepare the simulation of parameterized PDEs, where you do not only want the solution once, but you want to have it for a whole variety of parameters. And the major idea is sketched on the title page of this book that we had in 2017. So if you compute the solution in one parameter, then this is a point in your solution space. And you can consider now X at that point as a Sobolev space or a high-dimensional finite element approximation of it. And if you vary one parameter, then the solution lies, if the dependence on the parameter is smooth, lies on a curve in this high-dimensional space. If you have more parameter, then it's a low-dimensional manifold in this high-dimensional space. And this is what model order reduction explores. It tries to construct a linear space that has best approximation property with respect to the solution manifold. And this can be done in various ways. So one possibility is the greedy algorithm, the other one is to use the proper orthogonal decomposition methods, and meanwhile there are a lot of textbooks and reviews where a lot of these methods can be checked. So I give you the major ingredients where we have a formalism to look, let's say, at time-dependent PDEs, where LMU is a parameter-dependent differential operator. And the premise is that you have already a good solver, a finite element, finite volume, or whatever solver, such that for one given parameter you can compute the solution. Also, this might be quite expensive. So this is the machinery that you always need, and therefore we get never rid of classical finite element methods. And then the ansatz is that you construct this low-dimensional space with these best approximation properties with respect to the solution manifold, and then you project the original scheme, this one, into this low-dimensional space. This can be done by Galerkin or Petrov-Galerkin projection, and this gives you a reduced scheme, and then you can do fast simulations for a whole bunch of parameters. And this is, for instance, of interest in optimization problems, because in optimization problems with PDE constraints, in each of the optimization iterative steps, you need to compute the PDEs, and this has to be done a lot of times, and there you can benefit of this machinery. And the requirements in order to do that are reliable and efficient a posteriori error estimates. And this is not only to certify the method, but also we use this in order to construct these low-dimensional spaces. So for instance, in the greedy algorithm, or in the time-dependent case, we suggested the POD greedy. This is an essential ingredient in the construction process because you need an efficient error estimate in order to have this best approximation property. And then another ingredient is offline-online decomposition in order to make the reduced model in the end really efficient. And finally, for non-linear problems, this offline-online decomposition can only be done if you construct an approximation of the operators such that you can approximate in a fine decomposition, and this is, for instance, achieved by using empirical interpolation. So this are the concepts here. And just for those who do not really know about this offline-online decomposition, I explained it once. So if you have discretized your scheme, then you come up with a linear system where you have an implicit part and an explicit part on the right-hand side. So it doesn't matter whether this comes from a discretization by finite element or finite volume. So this is what you get. And then if you have given the reduced space, which is spanned by a basis with a small amount of basis functions, then of course you can project this into the low-dimensional space, and this is done as follows. So the low-dimensional solution is expanded in this basis. So these are the unknown coefficients depending on the parameter. And this is the reduced system, and the reduced matrices, which have now the small size, they are just given by these projections of the high-dimensional operators or matrices. So this is just projection into this space. And you see, if you compute these matrices here, so this is the sampling step, then in this formalism here, this depends on the parameter. So this means you would need to integrate on the domain, and this is a high-dimensional cost each time you pick a new parameter, and you need to do a little bit more to get rid of this high-dimensional cost, and this is what we call offline-online splitting. So offline-online splitting is the following. You assume that your operator has a particular form, namely what we call an affine decomposition, that you can write it as a sum of some operator that only depends on x, and a multiplication with a nonlinearity depending just on the parameter p. So separability in x and mu. And if this is the case, then offline you can compute these matrices, and you see that the dependence on the parameter is lost, and you pre-compute these small matrices. And then in the online phase, you just multiply these small matrices by this function, depending on the parameter, you sum it up, and you get this assembled matrix. So this is the technical part behind offline-online decomposition that you always need to do in order to really benefit from this method. And this is an important part that we need to keep in mind also for the process that I will talk about in the context of optimization problems. So for what I already indicated, the POD greedy method that we suggested quite some time ago, we have optimality results, and the POD greedy is for time-dependent problems, and it works in the following way. So we have an efficient a posteriori error estimator. We start with an empty basis and iteratively build a reduced space. And this is done by picking with a greedy algorithm a parameter that is worst approximated with the current reduced model from the previous iterate. And this is possible when you have an efficiently a posteriori error estimator that you can efficiently evaluate. Otherwise, it doesn't really pay off. So if you have picked this parameter, then you do a simulation in time, so you get a whole time trajectory. So these are a lot of functions in space for each of the time steps. And this is then compressed by using a PCA or principal orthogonal decomposition. So there is a singular value decomposition of the corresponding matrix where you put in the snapshots. So if you combine this is the POD greedy, and then you can actually show that you have this best approximation property in the Kolmogorov sense. So I define here the Kolmogorov width. So this is the best error with the best n-dimensional approximation space with respect to a given compact set, and this compact set in our case is this solution manifold. What you can prove is that if this best error decays algebraically or exponentially, then the POD greedy will produce an n-dimensional space which gives you the same algebraic or exponential decay with the same algebraic or exponential rate. So it's a quasi-best approximation result. And with this result, of course, the applicability of these methods relies on the decay of the Kolmogorov animals, because this is not always decaying fast. So we know that if we are in the case of elliptic or parabolic problems with analytic dependence on the parameter, we have like exponential decay, or in some cases only algebraic decay, but this is, for instance, not the case for hyperbolic problems where we have discontinuous solutions. And so this was also analyzed in these contributions, where the limits of these approaches are shown. And in these limitation cases of hyperbolic problems, it is clear, because this is the best approximation error that you can do with the linear approximation space, and it's clear that those problems are not accessible with these linear approximation schemes at all. So you need to really go towards nonlinear approximation methods in that case. And there are a lot of contributions which I will not talk about. So for the battery, we did simulations. So this is the model. So this is a coupled system of PDEs for the lithium ions and the electric potential, where these coefficients have different material properties depending on whether you are in the electrolyte or in the solid state of the battery. And at the interface between the electrolyte and the solid electrodes, the electrochemical reaction takes place, and this is modeled by the Butler-Vollmer kinetics, and you see that exponential nonlinearities enter into this boundary reaction term, such that this is a highly nonlinear PDE model, and you need to have all these ingredients. So we use the POD greedy, we use empirical operator interpolation in order to deal with these nonlinearities. And for a posteriori error estimate here, we have actually not rigorous a posteriori error bounds because of the nonlinearities in the system, and we rely on what we introduced in paper 2019 with the group of Carsten Urban, which is a hierarchical error estimator, where we use consecutive evaluations of reduced models with finer or lower accuracy, and use this for the greedy elements. So if you do that, then you can do some simulations. So this is for a finite volume scheme with 1.7 million degrees of freedom as a high-dimensional solver. And by using this technology, you get a speed up of around 280. So you reduce the computational time from 6.5 hours to something like 1.5 seconds. So this is very nice, and the engineers are happy if they have this reduced model and they can play with it. But it comes at a very high cost, because this offline phase is really expensive. So you need to solve time-dependent problems of that size multiple times. You need to keep all this in storage, which is a mess. And this is often neglected if people talk about reduced basis methods, that there is this enormous offline cost that comes with it. And this is the triggering point if you go towards optimization problems. So what is the problem here? And this is an actual example for a toy problem where we compute a PDE constraint optimization problem, and we have here on the y-axis the objective, so the difference of the objective function between the actual minimum and the computed one, and this is the computational time in seconds. And one of our models uses as a PDE solver a classical finite element solver. This is our full order model. And then we use classical reduced basis methods as a reduced order model. And if you compute this PDE constraint optimization with the classical descent method, then of course you do several optimization steps until you hit a certain tolerance and you think that you get a valuable answer of your optimization problem. And this is what the typical finite element simulation does. So you see that each iterate takes some time because the finite element is costly, but after some steps you are converged. Instead, the reduced order model, if you would just count the online time, you would have very short evaluation times and you would have like an immediate response of the solution. But if you take the offline time, then this offline time in a lot of cases is even larger than solving the whole optimization problem with just the standard method. So this is the classical point, and a lot of people do not talk about it, but this is actually what we want to deal with and where we want to be better. We want to profit from taking the structure of the optimization problem in order to do from the beginning a reduced model without offline phase. So this is the story. And why is it possible to be better? So this is now just a sketch for a two-dimensional parameter problem. So this is the parameter mu1 and mu2. And if you solve this PD constraint optimization and you start with a parameter in some area, then you see that this optimization outer loop will just evaluate your model on a certain path, and this is just a one-dimensional path in your parameter domain. And this one-dimensional path is even true if your parameter space is very high-dimensional. So if you think of 50 dimensions, then you still have just a one-dimensional path that you explore. And I indicated that we produce these reduced models, and these reduced models with discrete algorithms are produced in such a way that they have a guaranteed error accuracy on the whole parameter domain, and not just in the region where you use it for the optimization loop. And this is actually the point where you can beat the traditional reduced order models by taking into account that you only need the information in this area where the optimization loop goes. This is the major point, and what we do now is that we follow this optimization path, and whenever we compute a finite element solution, we learn from this and enrich our reduced model while going in the outer optimization loop. And the question is, how can you frame this and get also some rigorous analysis for that? So we start with this very simple PDE constraint optimization problem where we look at quadratic objective functionals, the quadratic part, a linear part, and parts depending just on the parameter and just on the state, which is then a solution of a variational problem depending on the parameter. And the overall problem is that you want to minimize such an objective functional. U is the solution of this equation with respect to mu, so you can also define this reduced objective functional just depending on mu, where mu is always the solution of this PDE, and you want to minimize this. And if you want to minimize such a problem, then of course you rely on classical optimization solvers. And these optimization solvers are typically descent methods, and either gradient descent methods or like the Newton methods where you use Hessian information. So what you need is that you should be able to explore, first of all, this functional, then the gradient of the functional with respect to the parameters, and also possibly the Hessian with respect to the parameters. And of course, this is quite an issue if you are in high-dimensional parameter space, and I will also come to that. And last but not least, we target that our PDE constraint is actually a multiscale or a large-scale problem, and we want to do specific investigation in multiscale methods in that context. So there have been quite some contributions on model order reduction in this context of PDE constraints, starting with this work of Ohlberger and Patera in 2007. But this was of the flavor first doing offline and just using the reduced model. And this went on, and just with the work of Yu and Mehrberg, and it started that people worked on models where somehow the reduced models should be created on the fly, and we were contributing now to that. So another group that's quite active in that is here the group which originated from the group of Farhat with Matthias Saar in his contributions. So what do? We want to use the rigorous framework of trust region optimization frameworks method. So what is a trust region method? So you want to find an optimum of an objective functional where you start in a point, in a parameter mu0, and you want to converge towards the optimum parameter. And the way that you do it is that you replace the original objective functional in each step by a so-called model function, mk, and you minimize this model function, and this minimization problem should be easier than the original one. And then you update, if you come to the boundary of a certain neighborhood of the last, in a certain neighborhood of the last iterate, and this neighborhood, this is the region where you trust your replacement model. And of course, in our case, now this model function here will be the reduced order model, which is not the exact model, the finite element-based model, but an approximation. And this is how we proceed. So what does change? So imagine this is the reduced order model, and what we do now is we go towards a so-called error-aware trust region method, where the simple let's say, ball around the last iterate is now replaced by the region where we trust the reduced order model, and this is measured where the relative error is smaller than a given tolerance, and this is the relative error with respect to the evaluation of the reduced objective functional. So this is where we want to have a control on. So you see that in order to make this work, we need a rigorous a posteriori error estimate of the gradient of the objective functional, or maybe in other contexts also of the gradient if you go to Newton type methods. And in that sense, you have a reduced model that is valid up to a certain tolerance in this region. Then you go with this very fast method until you hit the boundary. Here you need to re-evaluate with your finite element model. You enrich your reduced model, you get a better one. And then you also reduce this tolerance because you want to converge, so you want to send this tolerance to 0. So you get a region where the new model is valid. So you see that it, of course, has both original and the new value inside, but it is more narrow because the delta k is reduced. And then you do, again, fast optimization until you hit the boundary, and then finally you converge. So this is how the method works. And this idea was already in the work of Roy Wilcox in 2017, and we did some additional contributions to this. For instance, we went towards a non-conforming dual approach, what I will indicate in a minute, and in fact this gives sharper and accurate a posteriori error estimates, and we went also to higher order methods and did full convergence analysis, including also constraints on the parameters. So what you need in order to do that is we have the underlying PDE as a variational problem, which we call the primal state equation, and we just define the primal residual, and the error estimate that we do is a residual-based error estimator. And in order to evaluate the gradient of the optimization functional, we use the first order optimality conditions, and we can see from that we get the full gradient here by evaluating the gradient of the Lagrangian, and this depends on the primal solution, on the parameter, and as well on the dual solution. So in the dual solution, this is given here by the dual state equation. So it has the same bilinear form, where now the solution is in the second argument. This is why this is a dual. And the right-hand side here is the derivative of the objective function with respect to u. And if you look into that, you can write it out. You see that the solution of the primal equation enters into the right-hand side of the dual equation. Okay? This is classical folklore in optimization. So we need primal and dual in order to be able to evaluate the gradient, and we also introduce a primal sensitivity equation and dual sensitivity equation, which will be needed if you want to have higher order derivative information from the objective function. And okay, we now need to do model order reduction for all these quantities and also a posteriori error estimate for all these quantities. And this is actually what we did, and where we also now saw that you need to be careful and not do it just straightforward, because if you look at the reduced objective functional for your reduced model, then this is actually given by the Lagrangian evaluated in the primal, the parameter, and the dual. And if you write this out, and you see this is like just taking the reduced objective from the full order and replace all quantities by the reduced quantities. But then there is an additional part, which is the primal residual, where you take the dual solution as a test function. Okay, and if the dual is from the same space as the primal and you are in a Galerkin setting, then of course you know that this vanishes because of Galerkin orthogonality. But this is not the case if the space for the dual and the primal do not coincide and you do not test with the correct test function. And this is the case here because we want to trigger the reduced spaces for the primal and dual to optimally approximate those two equations. And in the examples that I show you here, these spaces are different, the reduced ones, and you need to take this into account in the analysis. So and this is what we did, and then you can do the whole analysis for all these quantities. You get a posteriori error bounds and a fully developed theory that we do in this paper, and I just show you the result for what we need for this trust region algorithm. So we need this estimate here in order to be able to do the trust region algorithm. And we see that the difference in the objective function between the finite element objective function and the reduced one can be given in that form. So you have a product of the primal residual indicator with some norm of the dual. So you see that somehow this error scales like the square of the error in the primal and dual. So this is what you expect for these kind of problems. And you can also derive a posteriori error estimator for the gradient of the objective functional, given in a little bit more lengthy formula. And the important part is that with these estimates, so these bounds, they can all be efficiently computed in this offline-online splitting fashion. So, which means every time we enrich the space, we also compute this U splitting in an efficient way and use these estimators that can be evaluated really fast, so without any overhead. So this is the major ingredients. And with all these ingredients, we can now formulate the overall algorithm. I don't want to go into all the details here. So this is in each step the subproblems with the current reduced model. This is the relative error that needs to be smaller than this given tolerance, this error over trust region algorithm, the update that we do. And then there are some rules here that also allow us to adaptively choose these accuracies that we have on the error-aware region in the different steps. And for this algorithm, in the end, we can show that actually with this technique, you always converge to an accumulation point, so to a local minimum. We do not guarantee convergence to a global minimum necessarily.
Is this a deep result or is it soft analysis?
What?
Is this a deep result or is it soft analysis? What's the tool to prove that? Or will you give
It uses the theory that you have in optimization theory, of course, but you combine it with the control, the error control by the a posteriori error estimators that we have. So this comes together. I mean, look into the paper and decide yourself. Yeah, so the new part is also that we have constraints on the parameter, and this is why this projection comes into here. So this is so if you would not have a constraint on the parameter, then you would just have the norm of the gradient, which is 0 in the limit. But this is just reflecting that we have parameter constraints. Okay. So with this being said, we have cooked up a model problem where we looked at the ground floor of our building. This is actually our common room, and this is the childcare room. And from this ground floor, we cooked up this model problem where you want to have a desired temperature in the childcare room, and the parameters that you can optimize are all the heaters in the building and all the conductivities of the walls and windows. So you should look at this. So this is heat conductivity. You see that we parameterize all the doors and windows, so these are parameters. And then we have a lot of heaters, so these are the sources. And if you put one heater in, then this is like the heat distribution with the simple Poisson problem model, and this is the dual solution that you get. So this is the kind of problem that we cooked up. And with this, we had a toy problem where we could plug in up to 46 parameters and testing our models with this. So this is just one result for different tolerance, and what you see is that the red curve, this is what you classically get with a BFGS optimization solver. If you just use the traditional finite element as a solver for the underlying PDE, and I told you that in the beginning, if you have the classical offline-online, then you would go offline like here and then down. And what our method now does is that at the first stages, you follow more or less the finite element solutions, because, I mean, your reduced model is not rich enough and has not enough information, and you just always hit the boundary and you need to enrich. But at a certain point, it collected a lot of information, and then it turns off and has this fast convergence that you expect from the reduced order model. And this is really starting with an empty space in the reduced model. So everything that you learn is just from the trajectory that you pass in the optimization step. Okay, this is concerning the global reduced model. And now we want to go towards replacing our underlying variation problem with a multiscale model. So everything stays again, but you should imagine that this is now a parameterized multiscale model. So also the microstructure is depending on the parameter. And I will come to examples. And of course, the bottleneck is that for very large-scale problems or multi-scale problems, the global FEM is not the correct approach toward that. So we want to combine this with some kind of localized reduced basis method or multi-scale method. And there is, of course, a whole slew, and we saw this quite several times from the different areas, from the reduced modeling area, from the multi-scale area, or also from the domain decomposition area. And so I will now go towards a specific approach, which is very close and related to the reduced basis LOD, which was done here by Patrick Henning with Asier Abdul. And if you want to look into a general framework and how you can cast all these methods into an abstract framework, then we have this recent review paper where we give somehow a unified framework for all that. So the unified framework, just in a short presentation, is always based that we have a global solution space that somehow we decompose into local spaces, VI, and then we compute reduced models for these local spaces with a reduced dimension, and then we, of course, construct a reduced global space by going back and concatenating all these local spaces to the global one. And depending on how you choose this decomposition in the spaces, you can insert all most of the known multi-scale methods into such a framework. And of course, if you have then constructed this reduced space, then just by projection you get your reduced model, reduced multi-scale model. So this always depends on how you do this space decomposition, and this is mostly using multi-scale and domain decomposition ideas. And there is the question of how to construct reduced spaces, what we call localized training. So for instance, the LOD step for correctors is like a localized training step. And then, of course, we want to, in the context of parameterized problem, to enrich our spaces adaptively, and this is what we call adaptive enrichment. So all these contributions come together, And I now come to the LOD. So this is now classical for all in this room. So we have to split our computational domain. So we have an underlying fine space, finite element space, an interpolation operator, and the fine part, which is the kernel of the coarse interpolation operator. And in that way, such a fine solution can be decomposed in the coarse and the fine part. And we have this A-orthogonal composition. And the only part is that now everything is parameterized, and we saw these parameterizations or these changes in the local problem and defects or uncertainties also in other talks. So this gives rise that this decomposition has to be done new for every choice of the parameter actually in this context. And this is why, of course, model order reduction now plays an important role in order to do this efficiently. And you all know that there is the additional localization step where you go towards patches, and then you compute this element-wise by solving these corrector problems, and then you get the multiscale space by the identity minus the corrector, which is the sum of the element contributions of the corrector. And of course, you have the decay, exponential decay. I don't. Then we go into Petrov-Galerkin setting, so we use this space only for the approximation of the, only as a trial space, and we use the original finite elements as a test function. This is all here. And I want to give now some insight how we use this in the model order reduction framework in order to make, in addition, the reduced order model. And we do not only use reduced order model for the corrector problems. This was done in the RB-LOD by Patrick Henning and Assur. But we want to do it for both the macroscopic coarse-scale problem and the local corrector problems at once. And this was done with Tim Keil and Stefan Rabe in this work. And the essential part is that we now frame the LOD a little bit different and come up with a two-scale variational formulation of this problem. So this is now what you do. So in the sense of our abstract framework that I showed you before, we want to come up with one single space that has a decomposition. And in this case, it has a decomposition in the macroscopic like finite element space and the corrector spaces. And we can associate a norm with that, which is just the H1 norm of the macroscopic part and the sum on the H1 norms of the correctors. And then we define a two-scale bilinear form where now this U and V here encodes the whole LOD solution. So it encodes in the first component the macroscopic part, and in all the other components the local corrector parts. Okay, and the same is for the test function. And of course, if we define this as a bilinear form, so you see that the first one is actually related to the coarse LOD problem. So if this is equal to your function on the right-hand side, where you just use the macroscopic test function, so this equal that, this is the coarse problem, and this equal to that is exactly the corrector problem. So if this is this difference is 0, and then you have to write correctors. And this means that if you write this variational problem in that way, this is an all-at-once problem for solving the LOD. Okay, and it has some very nice. So this is a nice approach, not with respect to solving the LOD that way. You don't want to build this huge matrix and solve it at once. But it's nice. It's nice because you get immediate a posteriori error estimate efficiency upper and lower bound, because you are now with a traditional substable bilinear form. So this is what you can then show is that the solution of this variational problem is actually giving you, so it's uniquely defined, and it gives you the coarse component and the local correctors of the LOD. Okay, and so if you
can I ask, what's the T's? Are they overlapping subdomains, or are they elements, or what are the T's?
So these T's are the macro elements.
But non-overlapping.
Non-overlapping. So like in the LOD, but of course, in the subproblems here, you see that this is AUT, so you're restricted, but this one is on the whole domain. Okay?
So you need to solve global problems, or you need to solve local problems for those?
So in the end, we use here the same technology that we do
With cutoff.
This local truncation with a certain step.
And F is, it depends on the right-hand side.
This is the right-hand side from the original problem.
Ah, okay, no, the F means fine. Okay, it doesn't mean...
F, this is the fine component. Okay. The fine component on element T. Okay. So if you go back... So it's actually, so the first component of this vector is this coarse part, and the second one are the element contributions of the corrector. Okay. And also, the same as in the LOD, you can use different sizes of oversampling layers in that bilinear form. And actually, so I will show you, so this parameter k that we have here, this is the size of the oversampling layers. So if we do now the model order reduction, we go in a two-stage procedure. So in the first stage, we do the same as in the RB LOD of Henning and Abdul. So we first actually just compute the local spaces, the reduced spaces for the corrector problems. Then with this reduced spaces, we build the system for the whole variational problem, where already for the local corrector problems, we just use the reduced order models instead of the full ones. And then we do snapshots and compress, and we get an overall reduced model for that. Okay, and if you have this overall reduced model, then for a new parameter, you get at once with this very low complexity the whole LOD solution for a new parameter, including all correctors. Okay. And the interesting part is, of course, and this is why we do this two-stage step. If we did the first stage, then we can throw away all the computed in fine-scale information, and we just keep the low reduced matrices. So this is the storage benefit. And of course, this first step can be done fully in parallel, because all these local problems are completely independent. Okay. So this is the nice part with respect to the implementation and the benefit, and what we need is a posteriori error estimate in order to make all this procedure framework work. And this is now quite easy, because in this new framework, so this is the solution now with all these component cores and defined correctors, you get by standard classical folklore this a posteriori error estimate, which is a dual norm of the residual, weighted by 1 over the inf sub parameter, and the inf sub parameter here is, so gamma k is the inf sub of the original bilinear, coarse bilinear form of the LOD, and with this construction you get this factor square root of 5 worse inf sub constant. Okay, so and this of course can only be achieved if you I come back to that. And this is why we have this rho parameter here. If this rho is chosen in the right way, so this is a stabilization parameter, it should be larger than 1, and we get this substability of the bilinear form in this optimal way if we choose rho to be the overlapping constant of the patches multiplied with the contrast of the original bilinear form. So this is also in the paper. So this is how you choose this stabilization parameter, and then you get this substability, and you can get the a posteriori estimate. And of course, the same applies towards the dual problem. If we now go to the PD constraint optimization, and we recover that we have the primal estimator and some dual part, which is again of the same form like the negative norm of the dual residual. And we can do the same to get an error estimate on the objective function, and actually you see that these formulas are the same as in the global case by just replacing the estimators for the primal and the dual by just using this relational framework. So this is what we can get. And what you also see, so this is the typical what we expect, and then there is some part here, and this is called the truncation part. And this comes from the localization of the LOD, so this part actually is 0 if you would use no truncation of the corrector problems. And the error that you do by localization that appears up if you do a simple bound on that, you see that you get again this exponential rate that you have from the LOD local truncation. So in the numerical experiments, we always assume that we have chosen these overlapping layers large enough such that we can neglect this term. So we do not consider this in the computations. Okay, and what we then cooked up is a model problem, which you can consider also an optimal control problem. Actually, we fix afterwards one configuration of a multiscale diffusion field, which is the U desired, and of course we want then to optimize with respect to the parameter in order to get the solution close to that. And in this case, we have these blocks. In each of the blocks, we have two microstructures, a coarser one and a finer one. So this is with these small dots, but very fine scale structure. So you need really high resolution to resolve that. And the overall field is just a linear combination of all these, which means that your parameter space in a linear combination is 32. So we solve this optimization in a 32-dimensional parameter space.
So each microstructure depends on mu or not?
So in that sense, we have two kind of microstructures, and we take a linear combination of that. So this means you get a linear combination of two microstructures in each block. And this combination is different in all the blocks. Okay, and you see here in this example, in the middle region, we have lower diffusivity than in the other regions. And if you do this whole computation, so what you see here now is a computation where the fine mesh, in order to resolve everything, would have 16 million degrees of freedom, which is not feasible with finite elements anymore, so we could even not do these calculations. And 1600 coarse elements, and these are the 1600 coarse elements. And in this procedure, the local spaces are adaptively enriched, which means that in the end, in this optimization problem, this is the basis size of the local spaces. So you see that in some parts we have like 3 basis functions in a coarse grid, and in other ones we have like 12. And if you see where this enrichment takes place, this exactly fits somehow with the boundaries of these coarse blocks, where the LOD does not really do a good job. Okay.
But doesn't it mean, if you look at the next slide, that the fine microstructure is basically not doing anything? Because in the interior of the domains, it doesn't need very high basis. So
yeah, this means that.
So what if you turn up the variability of the fine ones?
Yeah, I mean, then of course this would go up. So here you would expect that inside this block we have these two microstructures and linear combination, and what it shows you is that with 3 basis functions, this is well captured. Okay. So this is the simple part. Okay, and so in this example you see that now the trust region with the PG LOD is the reference solution, because we cannot do finite element. And this is the time that it needs, and this is the number of local sources that it needs, and the number of coarse sources. And the final version that we come up is this relaxed trust region to scale, and this then has this overall computational time, and you see that the most effort is then just with the reduced models that you evaluate. And also what you see is that the outer iterations with this relaxed version goes down at just 4 outer optimization iterations we come to the solution of it. So very nice results. So I'm close to end. We did the same, not just with the LOD, but we worked also with our horse, which is the localized reduced basis multiscale method. So I wanted to present LOD in this audience, but this method in the context of optimization is here, and we work also on combination of local training, where we use this randomized rangefinder, which is close to what you presented, based on this work of Boer and Smetana, where we currently work on such general problems. And we go also to time-dependent problems and even in very complicated PDE situations, like in this oil recovery. So these are two papers where we employ machine learning, and also machine learning in this paper where we use this hierarchy of models in order to get certification for the machine learning part. And what I also want to indicate in this new paper here, we really go to inverse parameter identification, where we do not have a low-dimensional parameterization of this diffusion parameter, but a high-dimensional field. And in that case, you need to do not only state reduction, but also parameter space reduction simultaneously. And the clue how to address this is in this new paper. So thanks a lot for the